the irreducible representation of highest weight Steinberg weight plus W times rho, and then I put a bar over all of this to make it an object of O instead of an object of curly A. I'm going to define delta W to be the same kind of thing starting from a Weil module, and nabla of W to be the same kind of thing starting from a dual Weil module. Okay, so here, here's some key features of this category. One is that these objects, LWs, they're simple objects in this quotient abelian category, and they're all of them. So these are the simple objects in category O. So if you're not used to the idea of thinking of simple objects in an abstract abelian category, it just means that it has no sub-object other than itself in zero. That's the same as the definition for representations. And this is already, I mean, this somehow is, this is already supposed to be something that makes you feel like this is a little bit more approachable. In particular, there are only finitely many simples. This is, of course, very different from the representation theory of G, where the simple objects are labeled by dominant weights, and there is infinitely many. Every object in category O has finite length. So some of this is going to look. I wrote down some list of properties, and then Yvonne wrote down almost the same things. And I thought I should like renumber mine to match his, but I didn't take notes in this talk, so anyway, I didn't renumber the list of features of category O. Okay, every object in category O has finite length. And so it makes sense to ask about multiplicities. And if you take one of these deltas, so if you take a delta, I'll call it X, and you look at the multiplicity of a simple object in it, if that's non-zero, then there's a constraint on what the labels can be. So X and Y here are both elements of the Weil group, and the condition is that this forces Y to be larger than X in the Bruja order. So in particular, there's a well, let me say something about projectives. So category O has enough projectives and injectives. So in other words, every object is a quotient of some projective object and a sub-object of an injective object. This again is very different from the full representation theory. In the full representation theory of G, well, if you're looking at finite dimensional representations, you don't have either projectives or injectives. If you look at infinite dimensional representations, you do have injective representations of G, but they're never, there's no such thing as a projective algebraic representation or projective rational representation. But these there is such a thing as a projective pro-rational representation, yes. But these things are finite length. Projectives have a filtration whose subquotients are these deltas, and injectives have a filtration whose subquotients are the nablas. And then there are various other properties that are important, but maybe I'll mention just a couple more things. I want to mention the extreme cases. So in the Brewer order, there's, the minimal element is the identity element of the Weil group, and then there's a maximal element, which is the longest element. So in both of those cases, you can say something a little bit more. So for W naught, which is the longest element, in this case, it turns out that the irreducible and the delta and the nabla all coincide. And at the other extreme, so let PW be the projective cover of LW. Well, the extreme case where we can just write this down really right away is when W is identity element. So PE is actually just delta E. Okay, so in my third lecture, we're going to come back to this and we're going to study PW naught, which is in some, well, I don't know if it's the most complicated projective, but it's more complicated than this one, and it has a lot of information. Okay, so in the last 15 minutes, I want to tell you a little bit more about some of the ingredients that go into understanding the structure of category O, and I want to sort of briefly sketch the proof of this. Oh, sorry, not the filtration thing, just the existence. So that's what I'm doing. Okay.
Pramod,
yes.
Is this a highest weight category?
Oh yeah, it's a highest weight category. Yeah, sorry, I forgot to mention that. What I've written down on the board, it's not so far from just being the definition of a highest weight category. Yeah, so O is a highest weight category. Okay, so part 3 is about translation functors. Okay, so I need a little bit more notation. So part 3 is going to be back in the setting of representations of algebraic groups. So it has implications for category O, but at least the beginning is more about just groups and representations. So I'm going to start with a simple reflection in the Weil group. And then I want to let pi s be the corresponding fundamental weight. So in other words, this is a dominant weight which is characterized by the property that pi s paired with alpha check equals 1 if alpha check is the simple co-root corresponding to s. And 0 if it's a different simple co-root. Okay.
Dear friend, what is that character you're drawing that looks like a W top with
it's a pi, but it's an alternative form of the letter pi, which in LaTeX you make by writing \var pi, and like too often people pronounce it as var pi when giving a talk. That's not its name. Its name is pi. So it's a letter pi, but it's an alternative form. So, yeah. Yes, I'm sure it's not var omega. Yeah. Yeah, and you, like the worst thing you can do is typeset it by typing like \overline omega. That's definitely not what it is. Okay. Okay. So yeah. Anyway, so it's a dominant weight. So what you should think of is like for SLN. Yeah. For like maybe it's a little bit easier to say for GLN. If you take a weight that's a bunch of ones, comma, a bunch of zeros. So that's not a weight for SLN because it doesn't add up to 0, but it's a weight for GLN. Those are the fundamental weights. That's the typical thing. Okay, and now I want to define another block of representation. So not the principal block, but a block labeled by this simple reflection S. And this is going to be representations whose composition factors are of the form L of mu, and I have to tell you what kinds of things are allowed for mu. And it looks similar to what I had before, except it has this fundamental weight plays a role in it. So it's kind of the same formula as before, but inside this expression there's something extra where there used to be nothing here, or there used to be a 0 here, and now there's a negative pi s. Yeah, so again, I mean the source for these formulas for mu, like the one I had up there and this one, these come from the linkage principle.
So what is P? Which one's P? Which one's rho?
Okay, yeah. So this one is P, and this one is rho.
And nu is just
yeah. So nu is just any weight. So little w is any element of the Weil group, and nu is any weight. Again, not necessarily dominant, as long as the whole thing comes out to be dominant. Okay, so now there's a pair of functors that go between the principal block and this S block, and I'm going to call them T superscript S and T subscript S. And here are the definitions. I'll write down the definition of T superscript S. So T superscript S of a representation is the following. You take the representation, you tensor it with the irreducible of highest weight minus W naught times pi S. But I mean, I kind of want to just stop here, except if I just stopped here, this might not be in the correct block. So what I want to do now is decompose this into direct summands and pick off the summands that do live in the correct block. And that's called projection. So PRS is project onto the block, which means pick out direct summands in the correct block. In this category. And then T lower S of V, the formula is very similar. Instead of tensoring with this irreducible, I'm going to tensor with the irreducible whose highest weight is literally pi S. And then again, I have to do this kind of projecting. So this time, I'm projecting onto the principal block. I'm picking out the summands in the principal block, and that's called PR0. Okay. So here's some facts. T upper s, T lower s, and T upper s are both they're both exact functors, and they're adjoint to each other on both sides. So each one is the left and right adjoint of the other one. And now I want to combine them. I want to let theta s be the functor from the principal block to itself, where I first apply T upper s and then I apply T lower s. So this goes from rep 0g to itself. Okay, so yeah, so I guess I've about 5 minutes left, so I'll tell you the main facts that we need about this. So this functor is sometimes called I'm never completely clear on the terminology. It could be called a wall crossing functor or reflection functor, but I think sometimes one of these words means like something else that you construct out of this. What's that?
You go onto the wall and off of it.
Yeah, yeah. So I guess this is translating onto the wall, and this is translating off the wall. So anyway, I guess I'll just call it theta s. So theta s preserves curly a and curly b. So it induces a functor on the quotient. So it induces a functor on category O. And here are the key features of this induced functor. So one is that if you take an element y in the Weil group and you multiply it by this simpler reflection, yeah, so this is part of the assumption on y. I want you to get something larger in the Brouwer order when you multiply on the right by s. Then there exists a short exact sequence that looks like this. I'm writing down a short exact sequence in category O, but if translation functors for algebraic groups are something you've seen before, then you recognize this short exact sequence. This is actually a short exact sequence of Weil modules. I mean, the corresponding thing, there's a completely analogous fact in the category of representations of G, and I'm just taking all those objects and regarding them as objects in category O to get this sequence. Number two is that if P is a projective object in category O, so is theta s P. And then number three is that let W be an element of the Weil group, and choose an expression in terms of simple reflections. Oh, sorry, I want to choose a reduced expression. Then you can use property 1 to show that LW is a quotient of the following objects. So I'm going to take delta E, and then I'm going to apply a bunch of thetas to it in the reverse order of the expression you see here. Theta S1 first, and then theta S2 up to theta Sk. But property 2, well, delta E Oh, sorry. Oh yeah, that's this is correct. Yeah, delta E is already projective. That was one of the facts up here. So this whole thing is projective. So what I've done here is I've produced a projective object that has LW as a quotient. Yeah. By two, this object is projective. So LW has a projective cover. So if you pick out a suitable indecomposable summand of it, then that will be projective cover of LW. So this is the sketch that that category O has enough projectives. Okay, so I think that's a good place to stop for today, and then tomorrow will be kind of a completely different topic. So it'll be like starting from scratch.
So, I could imagine two alternative ways to define this category O,
Okay.
and let me try to find out whether they give the same result. So, first way is take the usual BGG category O, which is defined over the integers, and then I can just reduce one.
I mean,
get the same for P bigger than Corsican.
the usual BGG category O. So, I mean, almost everything in the usual BGG category is infinite dimensional.
Right, but it's a category of modules of finite dimensional algebra.
Yeah, that's true. Yeah.
And I can reduce this finite dimensional algebra. And I would imagine I would just get the same. Am I correct?
Really? This is far from obvious to me. Maybe it's true, but
So second way how I could try to define it is instead of the G modules, I could take G1T module
yeah.
and take a similar territory. So doing it the same kind.
So G1T modules. I think the answer is no, but I mean, for computational questions, I mean, somehow, yeah, or at the beginning I said somehow the basic problem is computing the characters of these simples. So certainly that problem is equivalent to a problem of G1T modules.
But then I just take two small pieces of different categories, they may be the same.
They may be the same. I think for the problem of computing characters or like computing multiplicities in this category O, I think I guess I'm not completely sure, but I would imagine that's equivalent to a problem you can formulate purely in terms of G1T modules, and that's maybe a slightly weaker statement than saying that there's some equivalence of categories. But that seems likely.
So we define this category O starting with the principal block. Can you do the same thing with the other blocks, the Z, S? Did you get?
Yeah. One feature of the principal block is that it's an example of a regular block, and these S blocks are not regular. So regular means that so this is a formula for what's usually called the dot action of the affine Weil group, and the question is how big is the stabilizer of an element in the finite Weil group of some weight in this block. And so if you do it with any other regular block, you can do something similar with any regular block, and you'll get more or less the same thing. If you do it with a singular block like rep S, I mean you get something a little bit different. And maybe I'll discuss that more in the third lecture. So.
Did you say that Serre quotient category is always abelian, or if you start with an abelian category, you get an abelian?
So if you start with an abelian category and a subcategory which is a Serre subcategory, and that means it has to be closed under sub-objects, quotients, and extensions, then you can do this construction, and the output is always in a abelian category.
So this construction, you can sort of realize it in terms of finite dimensional algebras.
Yeah.
And so this third category can be realized as an item problem times an algebra times the item problem.
Yeah, that's a good way to say
That
it.
gives you all the properties
Yeah.
of that. So it's that's definitely.
Yeah.
I'd like to change just a few words in the key features.
Okay.
And if I, let's say, like, we have in number 3, and instead of saying LW is a quotient of apply all these, I'd like to say, I've got a Schubert variety that's an image of a Bose-Hamilton. And then, instead of saying it's a projective, I would say Bose-Hamiltons are smooth.
Yeah, this is tomorrow's lecture.
Okay.
Other questions?
Is theta squared, this is idempotent?
No. It's more like no, it's something like
It's taken on an irreducible. It's not.
yeah.
Because you get the irreducible and irreducible.
Yeah, that's right. Yeah.
I guess I'm a little confused in the notation on the key feature number 1. There's like several S's, I think.
Oh, sorry. This is short exact sequence.
Oh, I thought, okay.
Sorry. Yes.
Can I ask you to introduce your assistant one more time, in case people want to ask him?
Oh yeah. So it's Shotaro Makisumi, who's right there.
I think you should work everything out for SL2.
Oh yeah. Also, there's a typo in the. I mean, it's more than a typo. It was more like a thinko, I guess. So in one of the problems, I said something to construct a particular object in category O by taking the p tensor power of the representation of highest weight 1, and then taking its image in category O. This gives you a well-defined object in category O, but not the one I intended. So a bonus question is to figure out what this is. The one I intended was this. So.
Questions? Okay, if not, let's thank the audience.